Right. So the previous session was in about simple harmonic motion. So we have expanded the force in Taylor series. And the conditions we have imposed is there is no force at the origin. All higher order derivatives are 0 and first order derivative is a negative constant. So these are the conditions we have considered. So the resultant motion is another condition we have considered is this force is cyclic force or conservative force. So this can be written as a negative gradient of some potential. The result is this potential can be written as so this force is actually minus kx. So this is the if you include all the assumptions, the resultant force is minus kx. The force is directly proportional to the displacement and oppositely directed to the displacement. So force increases as the displacement from mean position increases. So if you pull it more and more, the restoring force will be more. And force is opposite to the displacement. If the displacement is away from the origin, the force will be towards the origin. Okay. And at the origin there is no force, so the object continues its state of motion. Whatever velocity it gained or acceleration it gained till this point will be continued further. And if you see the solution of this differential equation, so m dou square x by dou t square is equal to minus kx. So if you rearrange this, the equation becomes dou square x by dou t square plus k by mx is 0. And if you verify the dimensions of this, it will have inverse of square of time dimensions. And I am taking where omega is root k by m. So I am introducing a factor of 2 pi by hand. When we check the dimensions of this, let's say units of this is distance by time square, and the other term here you have units of radians multiplied by distance. So if you consider the units, there is a factor of radians coming excess into this equation. That's why we consider only dimensional formula to match equations. So whenever you add two terms in any equation, the dimensions of each term should match. Okay, so the dimensions of this one is L by t square, the other one is also L by t square, since radians has no dimensions. Angle is a dimensionless physical quantity. Okay, so this equation is dimensionally valid. So now the solution of that equation, dou square x by dou x square dou t square plus omega square x is 0. This is the equation we are considering. And the solution that we obtain is one possibility is sin omega t. Let's say, I mean, even cos omega t is also a possible solution. I'm considering one of the possibilities. So let's say x is a sin omega t. Then velocity is dx by dt, which will be omega a sin a cos omega t. Acceleration is minus omega square a sin omega t. This is minus omega square x. I mean, that is what this equation is. d square x by dt square is equal to minus omega square x. Okay, so if you keep on applying these derivatives, you'll have infinite possibilities. So what kind of motion is it and how to generate it is a matter of discussion now. So here you have a variation in displacement. So time variation of displacement is velocity. Velocity is non-zero. And you have a variation in velocity as well. Time variation of velocity is acceleration. That is also non-zero. And if you keep on differentiating with respect to time, other terms are jerk is di by dt, which is minus omega cube a cos omega t. And if you further differentiate it, jolt, which is dj by dt, which is plus omega power 4 a sin omega t. So like that, if you keep on differentiating that, you'll get infinite possibilities for that. I mean, everything is varying. Acceleration is varying, displacement is varying, velocity is varying, acceleration is varying, jerk is varying, jolt is varying. If you go further and further, all terms are varying. So what kind of motion is it? I mean, how to generate it is a matter of discussion. Right? I mean, we know constant velocity. I mean, if you maintain constant velocity, that is okay. Then acceleration is zero. But if you maintain constant acceleration, there will be a change in velocity with respect to time. And if acceleration is also changing, so it's almost a complex motion which cannot be imagined with conventional knowledge. Right? So this complex motion can be studied or generated using circular motion. I mean, this is a periodic motion, and the best known periodic motion in our daily life is circular motion. When an object travels on a circle, the motion repeats as a function of time. So this is the best known periodic system, and if you map this simple harmonic motion with this circular motion, so then let's say I'm keeping a mirror here and this is a track. So somebody starts from here and keeps on traveling along this path. So then image of the person on the diameter will move from here to here, and in this path it moves here, and then when the person travels in this track, it moves in this direction and in this track. So this is the resultant motion of the image on the diameter. So when a person executes circular motion, the image of the person on the diameter of the circle executes simple harmonic motion. So if you map both of these, let's say for one complete cycle the displacement is lambda. The total displacement for one complete cycle, let's say it is lambda, and then angular displacement is 2 pi. So when the person completes one complete cycle, angular displacement is 2 pi and actual displacement is lambda on the diameter of the cycle. So if I consider very small displacement, let's say here, let's say I call this as x and I call fractional displacement as x and fractional angular displacement as phi. So then for lambda displacement you have 2 pi as angular displacement, and if for x you got phi. Then what is phi? Phi is given by, the fraction of the angle is given by total angle multiplied by fraction of the distance. So let's say out of 1 unit, if you have 0.1 units of displacement, then the angle is also 0.1 fraction of the total angle. Okay. So like that you can map the simple harmonic motion with the circular motion, and just to confirm that the system has periodicity, we introduce 2 pi. Here also we have introduced, actually what is this? 1 by time square is actually nu square, frequency square. We have to write nu square here. Instead of nu square, we are writing omega square. Right? So we are introducing a factor of 2 pi by hand. The 2 pi factor is coming just to represent the periodicity in the system. With this kind of 2 pi you will come across so many places. Even in quantum mechanics, instead of h you will be using h bar, which is h by 2 pi. And instead of lambda is h by p, you will be using, otherwise p is h by lambda. Instead of this, you will be using p is h bar k. Instead of E equal to h nu, you will be using E equal to h bar omega. So like that, a factor of 2 pi is introduced wherever you have this wave motion or any periodic systems. Wherever things are repeating, to represent that periodicity, that system is having some periodicity, that information is represented by using this factor 2 pi. Okay, so wherever you see this 2 pi, and that system has some inherent periodicity, that must be remembered. So all these differential equations are unit wise there is a discrepancy, but dimension wise they are clear. Okay. So that's about simple harmonic motion, differential equation. So the next topic is time period of pendulum. So I'm considering that time period of a pendulum. So what is going on here in a pendulum? We are pulling it from its mean position away. So there will be a gravity acting on it downwards, and let's say this angle is theta. So this can be resolved into 2. This angle is theta and this is a perpendicular component. So this component will be mg cosine theta and this component will be mg sin theta. So when you resolve any angle, the component connected to theta is cosine component. The component perpendicular to that is sine component. Okay, so this is mg sine theta and this is mg cosine theta. So here the tension in the string will be balanced by this cosine component of the weight of the bob. That means what? The string remains stiff because of the weight of the bob. That too, cosine component of weight of the bob. Otherwise, it would have shifted up or down. So the string maintains its length constant because of the weight of the bob. And here we are considering non-stretchable string. So the length is fixed. So now the contribution to force is coming from the sine component, mg sine theta. The force is mg sine theta. What is the differential equation? So dimension wise, this is clear. F is mg sine theta, no dimensions. Okay, so this is the force equation. So we have to write right. So we have considered a simple pendulum here with length L and bob as a point object. So assuming the pendulum bob as a point object and length is constant, and when you stretch the string to one end, what happens? Its height increases from ground, so its potential energy increases. Okay, so that component of potential energy is given by this mg. It can be resolved into two components, one along the length of one along the string connected to the pendulum, another perpendicular to that. So one component is mg cosine theta, another the one that connected to theta is mg cosine theta, other one is mg sine theta. So these two will get cancelled. So tension in the string is balanced by this mg cosine theta. That means what? The weight of the bob is ensuring the string to be stretched to its full length. Other component is contributing to restoring force. That mg sine theta component is contributing to restoring force. So we are writing that mg sine theta. So now I can write the torque as force multiplied by the perpendicular distance which is along the length of the string. So perpendicular distance from the bob to the center of rotation. I mean, this is almost like a rotatory motion with O as a origin. So this becomes mgl sine theta. So this is the torque. So now I can write so get a negative sign here. Okay. So since this is restoring force, okay, we'll get this. So now I can write tau as I alpha, which is moment of inertia multiplied by angular acceleration. So this becomes minus mgl sine theta, and I can write this as ml square moment of inertia, and alpha angular acceleration as d square theta by dt square is equal to minus mgl sin theta. So I is the moment of inertia of the bob. So what happens? So this d square theta by dt square is equal to minus, so m gets cancelled, l gets cancelled, g by l sin theta. So this is the equation you'll be left with. So if you write it, so d square theta by dt square plus g by l sin theta is equal to 0. So to write this in terms of standard differential equation, multiplying with theta dividing with theta, so it is d square theta by dt square plus g by l sin theta by theta into theta is equal to 0. So now, what is the dimensions of this term? So here you have, if you check the units, it is radians by time square plus other term is unknown, and here I have radians. So this term also has units of 1 by t square, and I am introducing a factor of 2 pi by hand, so I call this as omega square. So the equation becomes d square theta by dt square plus omega square theta is equal to 0. So since it is a periodic motion, I am introducing a factor of 2 pi by hand. So in total that becomes 2 pi by t is omega square. So in total, so here omega is g sin theta by l theta, which is 2 pi by t. So in other words, t is 2 pi root l theta by g sin theta. So that is the equation we get for the time period of the pendulum. And for small values of theta, when theta is very small, sin theta can be written as theta. So what have we seen? That Taylor series expansion for sin theta is what? Theta minus theta cube by 3 factorial plus theta power 5 by 5 factorial minus theta power 7 by 7 factorial. So like that the series continues, and when theta is very small, I mean when theta is less than 1, what happens? These higher order powers of theta will become even smaller. Let's say if theta is 0.1, what happens to theta cube? It is 0.001. So it reduces, I mean other term is 0.401. So like that the value reduces to very small numbers. So this can be approximated to theta when theta is very small. So how small it should be is a matter of discussion. So let's say prepare a table for theta and sin theta, and let's say sin 30 degrees, sin 90 is what? Sin 90 is 1, sin 60 root 3 by 2, 1.732 by 2, 1.732. So for 30 degrees is 1 by 2, 0.5. So these numbers are not matching. I mean, how small should we go? Let's say for 10 degrees. Sine 10 degrees is what? Search for it in Google. Sine 10 degrees.
0.173.
0.1732. 1 degree?
0.017.
0.173. So like that, however small you go, this number is not matching with theta. Sin theta value is not matching with the value of theta. So where is the problem? And how small? Even 1 degree is also not allowed. It looks like 1 degree is also not allowed. So then how small should we oscillate the pendulum? It's a matter of discussion. So the main problem here is theta value for all practical purposes or for all experimental conditions, theta should be considered in radians. Okay, so if you convert this number into radians, 90 is what? Pi by 180 into 90. So this is pi by 2. Pi by 2 means what? 3.14 by 2. 3.14 by 2 means how much is that? .57. So theta in radians is 1.57. So for 1.57, sin theta value is 1. Theta is equal to 1.57. Sin theta is 1. What about 60 degrees? Pi by 180 into 60. So it is pi by 3. So 3.14 by 3. So nearly that number is 1. So for theta is nearly equal to 1, sin theta is 0.8. So nearly matching. The numbers are nearly matching but not equal. So what about 30 degrees? So pi by 180 into 30. This is pi by 6. So 3.14 by 6. How much is that value?
0.523.
Okay, 0.523. Okay. What about 10 degrees? 10 degrees in radians.
0.174.
174. 1 degree?
0.017.
Right. So like that, so if you see, when theta is 30 degrees, theta value in radians is matching with sin theta up to first decimal. So even if you round it off, this number is 0.5, this number is also 0.5. If you require accuracy up to 2 decimals, 10 degrees is good number. So up to 2 decimals, these numbers are matching, 0.17, 0.17. So if you require even further accuracy, you may have to go for 1 degree. So for all experimental conditions, I mean, at least 1 decimal point accuracy is considered to be good. So we assume the small value of theta should be less than 30 degrees. So if it is equal to 30 degrees, good enough. I mean, we get theta value matching with sin theta up to 1 decimal. So the small value of theta, how small is? It should be less than 30 degrees. Okay. So So we have to ensure that theta should be less than 30 degrees throughout the experiment. So now we'll see, we try to design an experiment for this. So we see a method to design an experiment. Okay.